Well, they have our so a bunch of these, not all.
Okay, Michelle, can you hear me?
I can, yes.
Wonderful. So I'm gonna go ahead and let the two people in.
Fantastic.
They appear to be the same person, Scott and Scott. So, yep, I'll let them in and then I'll let people in as it goes, but I won't let you know. I'll just let them in randomly. And
just give me the cue of when to start talking.
Yep, the only thing I need to do is I'll start you on Facebook because we're still early, aren't we?
Oh yeah, I guess we are.
Still have about 10 minutes. Sorry, I'm good. Facebook.
All right, so to begin it will?
Oh, nope, I'll let you know. Okay. I'm going to go ahead and should be starting us on Facebook, but
why not?
I don't know, I'm having a situation here. Hold on.
Thank you very much, everyone, for joining us today. We'll get started in a few minutes, so just sit back and relax and let me regale you with tales of archaeological conservation. So, in a few minutes, as soon as Facebook cooperates with us.
Oh, man. Oops, sorry, I'm on speaker.
You're good.
I'll mute myself. Okay, Michelle, I'm going to have to log out and log back in. I'm sorry.
Okay.
Sorry about this.
No problem. Thank you for bearing with us. We're just trying to get the technical kinks out of our presentation today. So Zoom is not cooperating with us, apparently. I'm just going to kick the door open. How's everyone today? All right. Anyone have any questions on the onset before I actually get started?
Is it predominantly from seawater?
Yes, we will be discussing archaeological conservation in a maritime context, which means we're dealing with things that have been buried in the ocean. So mostly talking about our friend NaCl or sodium chloride, so table salt, which is also the predominant salt in the ocean. But there are other forms of salts, as we'll see.
Okay, you should be good to go.
All right, thank you very much, Christine. Well, welcome everyone. My name is Michelle Crepeau. I am the conservator for the North Carolina Maritime Museum, and As the conservator, my job is to essentially be the artifact doctor on site. My job is to help take care of all the stuff that you see in the museum in our collection. So I essentially identify problems that our artifacts are experiencing, like health conditions, so to speak. I will devise treatments and courses of remedial sort of tasks and things that we can do for them to try to make them a little healthier. And then overall, I monitor their long-term health to make sure that they stay in good condition for as long as we possibly can, so they can continue to communicate the information that we need to you, our visitors, so that you can continue to come here and enjoy them for as long as possible. And today I'm going to be talking about a topic that is very important, especially in the context of archaeological conservation that deals with maritime sites. One of the biggest issues we have to deal with in a maritime site is the fact that these things were buried in the ocean for long periods of time and that they are very salty as a result. And this discussion today will talk about why that is a problem, get a little into the science and the mechanisms behind exactly why that is a problem, as well as what we do as conservators to try to address the issues that we will talk about today. Before I get started, I would like to extend a big thank you to Captain Mark of H2O Captain Eco Tours and Charters for sponsoring our museum Zoom account and thus enabling us to present on a virtual audience on a virtual platform. So thank you very much to him and for all he does for us. And sit back, relax, and let us begin. There's a bit of lag. Okay. There we go. All right, bit of lag. All right, so first off, what is desalination? Desalination is simply the process of removing minerals and salts from one material, such as water or soil. You may be kind of familiar with this tangentially in the kind of idea of really industrial scale water treatment. So water processing, it's one of the things they do to sort of purify drinking water. You might even have this on a very small scale, especially if your water comes from a well system, where they do make sort of personal at-home filtration systems that accomplish this as well. And then, of course, I'm most interested in the context of archaeological conservation. So the kind of crude methodology that you see here on the left right here. All right, and why is desalination such a critical part of conservation for maritime artifacts? And that is simply because the ocean is a very salty place. It is what defines it as an ocean, as a body of water, as opposed to a lake or a pond or what we call a freshwater body of water. And of course, if your artifacts are sitting in this material for long enough, they too become very salty. And the type of salt we are most interested in discussing are soluble salts. So soluble salts are salts that are able to be dissolved in another medium, into a solvent. This can be a liquid solvent. It could also be a gas solvent. Sometimes it's even another kind of in between plasma or sort of partially solid, partially liquid state as well. But for the purposes of this particular discussion, we're most interested in the universal solvent water. So for all course and purposes, we're talking about salts that are specifically able to be dissolved into water. All right, and how are they able to be dissolved? This is sort of my representation of what dissolution looks like in sort of that process, using sodium chloride, aka table salt, aka the salt that is predominantly in the ocean as an example. So you can see that we have our salt structure as a solid that are represented by these little individual chloride and sodium ion atoms. And then you can see that a dissolution process is a breaking apart of this material and a dissociation into the solvent material. Water itself is partially, it is so universal as a solvent and so ideal as a solvent because it itself is constantly in a state of flux. It is very dynamic. It is not just our normal H2O, but it is continuously transforming itself into different types of what we call ions. Ions are basically variations of an elemental atom that have either lost or gained an electron. That includes hydroxy ions, as well as hydrogen and hydronium ions as well. And this dissolution process, this kind of slow dissociation from a solid and dispersal into a liquid is made possible by understanding some of the bonds that are at play here. So our sodium chloride as a solid crystalline structure are held together by very powerful bonds called ionic bonds. Ionic bonds are what happens when you have an electron. So just to kind of give you a review on how atoms are formed, we have our nucleus right here. Our nucleus is comprised of your protons, which are your positively charged subatomic particles, as well as your neutrons, which are neutral in charge. They basically just kind of fill out the mass. and then sort of orbiting it in these kind of cloud masses are what we call electrons. And these electrons are what really do the work of most chemistry. So what happens is that you have two types of atoms that are in contact with each other. One of them tends to be much hungrier for the electrons than the other, and will essentially steal an electron from its contemporary, thus transforming them both into ions, in which one has basically one more electron than its proton-centered complement, and the other will have one less electron than its proton-centered complement, meaning that one now has a slight positive charge because it has one more proton than it does electron, and one has a slightly negative charge as it has one more electron than it does proton. And so the bond is really happening. We like to see that these bonds are because they're sharing electrons. Well, ionic bonds really aren't so much a sharing of electrons. There's a little bit of sharing involved, but really it's because you have two ions that are different charges that are then attracted to each other, kind of like two ends of a magnet, essentially. And that bond is what's really that attraction is what is holding them together. And it's a very strong bond. In comparison, water has something called a polar covalent bond. So a covalent bond, a normal covalent bond, is sort of our more traditional idea of bonds using shared electrons, where you have two electrons that essentially orbit both atoms. They both have a full complement of electrons as a result that match their proton number as well. So there's no overall charge. However, when you have polar covalent bonds, that's not exactly true. What happens here is that you have the electrons are shared between the hydrogen and the oxygen, for example, but the electrons are shared disproportionately. It's not an even sharing. Basically, oxygen gets more of a time share with the electrons than the hydrogen do. So they spend most of their time orbiting much closer to the oxygen molecule than they do to either the hydrogens. And this creates a very, very small charge that happens along this bond, where you have a slightly more negative center oxygen atom and slightly more positive sort of distal hydrogen atoms that are in sort of relationship to each other. So these are called dipoles. They're represented by a delta symbol, which you'll see right here. So this little lowercase delta symbol, and they basically talk about regions of polarity, so slight charges of these molecules. So this is what makes these bonds really special. There's also geometry involved because basically the lone electron pair essentially kind of push. Since the oxygen is such a bigger atom, it essentially pushes the hydrogens into this very particular geometrical pattern that also sort of increases this regional polarity. So you have one area sort of by the oxygen that's a lot more relatively negative than what's happening over by the hydrogen, which is a lot more relatively positive. So you end up with essentially a molecule that has two distinct areas of relative charge. It's not very strong compared to your ionic bond, but it is there. And this is sort of how these work. And to understand how they work intermolecularly, we'll kind of return to this drawing. So I'm talking to you about how these are bonded by very powerful ionic bonds here in the solid mass. So how is it that these sort of weaker dipole charges, these weaker polar covalent bonds, are able to break apart these very strong bonds between our solid molecules? And that comes down to the fact that it's really just a matter of the totality of all these small dipoles that add up. I found a really cool GIF online of this process, which I can't share because it's copyrighted, but it was really much like watching mosquitoes swarm on you if you go hiking in Fort Macon at the wrong time of year. It's just sort of this really kind of mass attack on these structure, and essentially the breaking of these bonds by the competition of all these totality of these smaller negative positive charges that are happening in the water, which allow for the structure to break down over time and allow for these atoms to essentially lose relationship to each other and break down into the water itself. And these are very sort of dynamic bonds, so you do have things that are regrouping constantly, breaking apart, but generally speaking, it's a process of water coming along. There's enough of it sort of ganging up on the bond between the chloride and the sodium, breaking that bond just by sheer numbers essentially, and then these two atoms separating, which we call dissociation, and going their separate ways in solution. So it's a very complicated way to basically say that's how salt breaks apart in water essentially. And you might say, okay, we now understand a little bit more about how the salt gets into the water. But then how does that dissolved salt get into the artifact? And to understand that, we have to talk a little bit about one of my favorite processes, if it would, there, diffusion. So diffusion basically is the movement of dissolved particles in another medium. So it's dissolved salt, in this case, in water, and how those move. Because they move in certain ways. They're not just higgly-piggly a certain mass. If you have essentially a mass that has a mass of a solvent that has slight variations in concentration, like you might have a region that has very high in your dissolved particulate matter concentration in a region that has very low concentration, then what happens is that particulate matter wants to move out, it wants to spread, it wants to be equally distributed. So it'll essentially flow from a region of higher concentration to lower concentration. That is what we call a chemical gradient. This is just sort of spontaneous action that is meant to spread out the concentration of these particular ions in solution. You might have also seen this in high school biology, done an experiment where you have something called a selective permeably selective barrier that you put in between a space and essentially compartmentalize two areas within a solvent, and then those materials will have to cross that permeable barrier. So that is also kind of an aspect of this, is that, but overall, it is essentially just looking at the movement of material dissolved in solution from an area of high concentration to one of low concentration, and essentially how quickly that occurs depends on several factors, mostly how much of basically how big the disparity in the concentration is between your dissolved solutes. So obviously the steeper that gradient is, the more concentrated area you have in one place versus less in another place, the more quickly that material is going to move and spread out, until eventually it becomes very shallow, it slows down and reaches what we call an equilibrium. So essentially where you have an equal amount of material spread throughout your solution. And chemical gradients are pretty much the predominant gradient that drives this action. There is another one at play. It's called electrical gradient. Since we are dealing with ions or charged particles, they have positive and negative charges. This can also be done by looking at areas of negative charges versus positive charges, where those charges want to essentially equalize and spread out and are attracted to their opposite counterpart. So that is another concentration gradient. We'll get into that a little bit later, but this is essentially the basics of diffusion. So you have basically the spreading out of material that wants to move essentially through things into things throughout to basically equalize it so that it's equally represented both in charge and concentration. Okay, so we kind of understand how it's spreading on the water. How then does it actually get into the artifact? And that kind of comes down to how porous your artifact is. How many holes are in it? How easy is it for that water and that salt solute to essentially penetrate that barrier of your artifact, which might be the surface of your artifact. Generally speaking, it's not liquid. It's not going to be just spontaneously permeable by itself. You do need some sort of hole or opening to allow this. And this happens in several ways, through corrosion for things like metal and glass artifacts, where basically you have material being eaten away. And so you have an interior space then exposed through essential loss of material. You might also have biological attack that affects a lot of organic materials that gets buried in underwater contexts. This basically means microbes, bacteria, algae, fungus, all those little critters that live on the subatomic level that are basically eating into your artifact. So wood, for example, this is a micrograph of wood structure. You can see these are cells within the wood structure. You can see these areas that have mass still retaining them, and then ones that are basically empty. This means that there's been some sort of biological life form that has found its way into the cells of the structure and eaten them out, essentially. So just left them sort of these very brittle whole structures where water can move through, and thus particulate matter like dissolved salts can move through as well. And then there's a lot of materials that just are naturally porous, that have natural holes in them. This could be a lot of things that are organic, like things made of leather or skin, and ceramics tend to have small pores as well. Anything that would have basically an air bubble or micro pocket in it is essentially what creates these little holes. So that's another way for water and the salt to get into an artifact. And there's just the forces of erosion, sort of the physical forces of being buried in an environment that is very dynamic, often like the ocean, where you have sand moving, you have water moving, you have little rocks and other material bumping into each other, where essentially you just have a mechanical breakdown of the artifact over time from these artifacts that also open it up as well. So kind of just demonstrate how this might look like in an artifact. So just to kind of set it up, we have an example of a metal artifact and a ceramic artifact that were found in a maritime context. These structures sort of represent kind of a zoomed in version of what's happening. You can see that this is meant to be the core metal. Maybe there's a thin crust of tarnish or corrosion on the surface. And there's also little cracks and pits that have been caused by corrosion over time that have opened up this artifact. Same thing with the ceramic, except especially earthenware ceramics like terracottas have a lot of natural pores in them. They're very holy themselves. So there's a lot of areas where this material can access these artifacts. You can see that the water, there's a lot of salt. Interiorly, inside the artifact, not so much. So just to sort of demonstrate this diffusion process, you can see the artifacts moving, or the salt here represented by the chloride ion, moving from the ocean, the overall solvent, into the artifact, which is an interior space that obviously has less salt in it at this point than exteriorly. So just that illustrate that diffusion process. All right, so your artifact is now full of salt. So what's the big deal with it being full of salt? Why do we care? Well, this is a multifaceted response and will probably comprise the bulk of this this talk. So, sit down and hold back. First, we have to understand sort of a little bit about the structure of salt. So we probably have referred to salts as salt crystals before, and that is a reference to essentially the three-dimensional form that they take as a solid. So those little sodium ions and chloride ions, when they form that solid, when they form those ionic bonds, they do it in a very particular structure that we call a crystal. It's a very rigid, very geometrically regular structure that is often very particular to the particular salts or the particular ions that are involved in its creation. And these salts grow. So they're really fun to watch. I'm sure some of you have seen, actually have an example. You can sort of watch those crystals expand and grow as all those ions come together and reform this crystal when they're not in a solution, essentially. There's multiple factors that sort of influence how big and how fast these grow. Things like ambient temperature, so how hot or cold it is in their environment, the atmospheric pressure, how much pressure is being sort of enacted upon them, as well as the concentration, how many of those ions are available to really quickly form a salt. Obviously, the more you have, generally speaking, the more you're going to get in terms of speed and size. And also the evaporation rate, if it is a salt that has been dissolved into a solution, also evaporation rate. So how quickly that solvent, that water, is being removed from the situation, and thus allowing those chloride and sodium bonds in this instance to reform, et cetera. So this idea, so basically the takeaways are that salts are crystals and those crystals grow. So once you have something in solution, and that solvent is removed, those crystals will reform. So you can imagine when you then have salt in your artifact, that can be kind of a big deal. So when we first excavate our artifacts, we have to be very careful, because if we excavate them from the ocean and they're wet and full of salt, we have to be prepared for the fact that that salt is going to do something called effloresce, or it's going to essentially recrystallize once that water has evaporated and the artifact is dried out. And what happens is those crystals expand and they're inside your artifact. All of a sudden, they are essentially forming these giant masses in spaces that they were never supposed to be in. So all these little pores, all these little like microscopic cracks and things where this water and these salts have managed to permeate in a solution form are now being filled by a solid, which is rapidly expanding and growing. And you can sort of see it, that micrograph depicts sort of the mechanical pressure and the changes is occurring. So as a result, you can imagine that you can essentially break your artifact from the inside out if you allow these things to dry too quickly and these crystals to grow too fast and too big. You can really damage your artifact. This is also a problem even after post-excavation. So even with materials that have been taken from the water, have been conserved or otherwise very carefully dried, it can still be a problem because soluble salts always remain soluble, which also means that they are affected by atmospheric humidity, or what we call relative humidity, RH. So basically how humid it is in the environment. Sometimes that atmospheric humidity can be so great that essentially resolubilizes your salt. Essentially that salt will essentially dissolve back into solution because there's so much water in the atmosphere. So you have this, and then once it solubilizes and that RH change, perhaps it gets a little drier, all of a sudden you have these crystals reforming again. And this is called efflorescence. And this over time, as you can imagine, as you have this as a process that is very cyclical, that keeps happening over and over time, where you have these cycles of crystal dissolution and then crystal regrowth inside these artifacts. You can also have instances where you start losing elements of your artifact. You can see some of the glaze is starting to pop off on the ceramic here. And this is a very good example from the Canadian Conservation Institute. So we have an artifact that was originally excavated from a very, very salty site. Obviously, it has all these crystals crystallized on the surface. It's been cleaned, it's been conserved. And then you can see over time, it's been kept in an area where there's really high humidity. And as you can see, those salts have reappeared, they have effloresced. And over time, you can see the totality of the damage and just how much of that surface detail we've lost. And this means, it's your glazing, it's your decoration, it's your painting, if it's an earthenware vessel like this. So it's really kind of the interesting things about the artifact that you could be losing because of the salt growth. So soluble salt recrystallation after excavation is a really, really big problem. And it's something that we definitely have to keep an eagle eye on in our collections. And outside of just sort of the physical aspects and the impacts, there's also the idea that soluble salts are really the building blocks of chemistry in a lot of ways. Soluble salts sometimes are able to change the environment that they're in, which can then impact your artifact. They are also able to help create chemical energy, so that diffusion that we talked about was a type of chemical energy, that movement. We'll get into that a little bit more detail in a little while. And they also, once they dissolve into solution and they're hanging out as ions, all of a sudden they become the raw material to help build other things, to help really transform our artifacts. So kind of an example of how salts can affect your environment is that salts can affect your pH, or basically how acidic or basic the environment of an artifact is. Sometimes it even means the surface of the artifact can become more acidic or more basic because of these salts. For the most part, salts are kind of the very broad definition. They are the byproduct of a neutralization reaction between an acid and a base, and they create a neutral solid product. So for example, sodium chloride is often produced sort of artificially in labs by mixing together hydrochloric acid and sodium hydroxide, which is a very strong base and a very strong acid respectively. And they create this neutral salt. So by neutral, I mean it has no pH value in and of itself. If you put it in solution, if you dissolve it into water, it is fully consumed, and it doesn't affect the pH balance. And pH, just to explain this a little bit more, means the power of hydrogen or the potential of hydrogen. And essentially it is a measure of how many of these hydrogen atoms or these hydronium atoms you essentially have free floating in your solution. Because essentially increases in hydrogen atoms or hydrogen ions are what makes something acidic, whereas increases in hydroxyl ions are what make them basic. And as you can see, water exists in all these forms at once, and generally speaking, there's enough of them that they kind of balance each other out. But it's when you start adding other things into them that sort of perturb the balance and start increasing the balance of hydrogen or hydronium or hydroxyl respectively, that you start getting changes in your pH, and you start making your solution very reactive in ways. All of a sudden, you sort of have these free ungoverned ions that are running around that can essentially cause changes in anything else that's in there. So that's kind of an idea of what a neutral salt looks like. But we also have special salts that are acidic or basic in and of themselves, which means once they are reacted, they form a solid. You put that solid into a solution of water, say, and they change the pH. They change the number of hydrogen or hydronium ions or hydroxyl items that are available. So an example is sodium bisulfate. So what happens here is that this is a product of an incomplete acid-base reaction, so an incomplete neutralization reaction. So instead of creating a neutral product, they create something that has the potential to be acidic. And the way I like to think about this and wrap my brain around it is because you see, whereas sodium chloride had essentially one atom of sodium and one atom of chloride, and they're pretty simple atoms. This creates what we call a molecular ion. So you have a hydrogen sulfate ion right here. And basically this means it's a big ion that can still be split apart into smaller parts. I like to think about it in terms of fractions. So you have a big fraction, which you want to simplify. And in a neutralization reaction, you would take the largest common denominator and simplify it down to its lowest form, essentially. But in a partial neutralization reaction, you basically don't take the biggest common denominator And you sort of are stuck with this thing in the middle that is only half simplified, that can be simplified further. So when you take this half simplified material, put it in solution, it dissolves, it dissociates, and all of a sudden this gets really rapidly simplified inside solution. And you can see that there's an extra hydrogen molecule hanging around. So that means that you end up with an increase in hydronium species. So you increase the acidity of your solution. And a basic salt is sort of the opposite, where you have, again, a very kind of unsimplified fraction, as it were, that has been created by this partial neutralization reaction that can then further be broken down once it's again in solution. But instead of creating more hydrogen and hydronium ions, it creates hydroxyl ions. So it makes a more basic or alkaline solution. And the most important, so that's kind of how they can affect the environment. That will come more into play a little bit later when we start talking about corrosion, as well as how we as conservators address some of these materials. Also, in terms of being the building blocks of chemistry, soluble salts are electrolytes, which are probably their most important role in most of the chemistry I deal with as an archaeological conservator, especially when it comes to metal things. So I'm sure you're familiar with electrolytes as being something you drink in a Powerade or Gatorade, et cetera, something that you chug down to sort of give you some more energy and to sort of replace a lot of the salts that you've sweated out after heavy activity. And what we're really, the parts of the electrolytes that what this is really talking about is an electrolyte is any dissolved particle that is able to conduct electrons. So these guys. So we talked about those a little bit earlier. So we'll just refamiliarize them that the way that they conduct these electrons is really through forming different types of bonds. So they form ionic bonds, they form covalent bonds, as well as polar covalent bonds in solution. And, you know, of course, these bonds are being formed sort of all the time, rapidly. They're changing who they're bonding to, et cetera, because again, you have your sodium or your chloride ions, for example, that are being surrounded by this multitude, being swarmed by the mosquito-like water ions that are trying to, you know, keep them with them. But they're also, you know, occasionally there might be a chloride ion that bumps into one or both of them, and so all of a sudden they have an ionic bond formed with another sodium molecule, or they have a covalent bond formed with another molecule themselves, or, you know, sometimes they even form things like hydrochloric acid and sodium hydroxide in solution as well. But generally speaking, this does not survive long enough to really affect the pH. And you might have other things in there that are in your solution as well. CO2 tends to diffuse into water, for example, and acidifies it over time by creating carbonate ions. So you do have these other species that are existing. And of course, you have water sort of transforming constantly into its various forms as well. So essentially you have all these electrons kind of moving around constantly in solution between these charged particles that are just sort of out and ready to form bonds with other things at all times. But generally it's kind of higgledy-piggledy. There's really no direction to it. It's just sort of free energy being passed around. That kind of changes though when you start to stick things into the water. So especially things that are made of a very kind of refined type of material. So something that is made primarily of one type of atom or one type of molecule. So things like iron or silver, things that we have artificially refined to basically be composed mostly of one type of element or another. In which case we certainly add in a type of directionality to the way that these electrolytes are conducting themselves and the way that they're passing around electrons and forming bonds with things. So it becomes a little bit less of a free-for-all and more of a relay race where your electrons are your baton that you're passing around. And this really becomes important in terms of either metal corrosion, when we have metal artifacts that are in salt water, or things that contain metals in them. Like sometimes, you know, we have glazes for pottery. Some of our glass contains metal additives to them that change their color or give them other working properties that this can also affect. But to talk about this, we're going to talk a little bit about galvanic electrochemical chemistry. I'm not going to go into it too far, but essentially when this happens, you have two artifacts of different materials or compositions that are touching physically in space in your solution, and or it can be also the same artifact as well, but you have slight differences in the composition on different sides of your artifacts, because it is pretty rare that we get anything that we artificially create that is 100% uniform, the same thing. There's always going to be little tiny differences, little imperfections, little other things that have snuck their way into that material. And this is going to create differences, electrochemical differences in your artifact or between the artifacts. in which case something we call a galvanic cell is formed. So a galvanic cell is basically a machine that essentially promotes oxidation reduction reactions, where basically transformation of one material into another by the removal of electrons en masse from one material and given to another one. And basically, who is the anode, and this is also known as the anode and the cathode, and who gets to play the anode and who gets to play the cathode is determined by something we call the electrochemical series, which basically is a measure of how good a particular material is at giving up or receiving electrons in comparison to hydrogen as their base metal. And so you can see that there is I did that too early. So you can see that there is an exchange of electrons that is occurring between our anode material over here and our cathode material, so zinc and copper in this instance, in which their physical connectivity is essentially inducing electrons to be passed from one to another. However, this would not exist if it wasn't for the fact that they were both sitting in a solution that contains electrolytes, because essentially this part, that touching, that physical connection, is really only one part of a circuit essentially. And what you really need are your relay players. So you need your moving anions, your moving cations that are in that solution actively transporting your electrons back and forth and basically replenishing the cycle, so you create the circular cycle or circular circuit essentially that is occurring, where you have essentially anions, for example, flowing towards your anode over here, which again is also an example of an electrical gradient. So basically what I wanted you to get out of this fact is that you have two materials that have different abilities to accept or give electrons that when they're in a saltwater solution will corrode, largely because the electrolyte is there to help complete a circuit that basically helps move electrons between the two and thus helps transform what they are. And we call this corrosion essentially. So this is just another example. Kind of using another aspect of this is that you don't just have electrons moving, you also have chemistry happening of these materials. And what you have is that you have an anode material, which is essentially being dissolved in part because of the movement of these electrons, being bombarded by electrons, which are essentially severing the bonds between those materials. And it essentially is disassociating into the solution around it. Whereas you have electrons being given to another material that is also being bombarded by electrolytes that have basically reactive components to them. And the cathode is essentially building or creating, taking all those little pieces out of solution and using them to basically build something new. So kind of illustrate, yes, so you have example of zinc grain structure and some copper crystals that you can see. And essentially what I want to get out of this is that you'll have one material that is essentially being dissolved or reduced and another one that is growing and creating and crystallizing essentially. So it's also not just electron being passed around circuit, it is also an idea that focuses around the loss of material from one material or the dissolution of one material and the growth and development of material at another site. And that material that is coming from another site is being pulled in from all those dissolved electrolytes that are around it as well, which are essentially the building blocks for new stuff. And kind of to illustrate how this all comes together, a little bit of everything is happening here. This is an example of a type of salt catalyzed corrosion that we often see with iron that has come from a saltwater environment. What happens is that you can see that these little kind of blistery things on the surface. These are what we call corrosion blisters. And these happen, first of all, because you have high humidity. So you have basically soluble salts, like this chloride salt, which is essentially being dissolved into the atmosphere or dissolved into atmospheric liquid. And what happens is you have kind of natural imperfections, natural little recesses, natural little cracks in the grain where this basically solution can basically accumulate over time. And the solution over time is obviously more reactive than what's around it. So what happens is you have these little pits that start to form where this where the solution has sort of formed a reservoir. And that is where you're having that electrochemical circuit being formed on a very, very small scale. And in that, you're also having, because you have such a high concentration of salts, You also tend to have a production of hydrochloric acid in these little tiny pockets, just because you have such a high, basically the chemistry pushes it towards the creation of what I kind of formally said was a very sort of minor element of most water with a hydrogen chloride. And you also have salts, you also have iron salts that have been made at these, so at your anox, sorry, oops, no. So at your at your anox sites, probably like the bottom of the pit here, you have this hydrochloric acid being formed. This hydrochloric acid in form is dissolving your metal structure. It is creating a lot of iron cations. Those iron cations are also interacting with your chloride at the more cathodic end of the site, and is building basically iron chloride salts. So iron chloride salts like ferrous and ferric chloride are themselves acidic salts. So we talked about that a little earlier, is that once those kind of go back into solution, they also raise the pH. So you have this very sort of cyclical action of acid formation because of these reservoirs of collected salt solution in these artifacts that create an acidic environment that basically kick off your galvanic corrosion. But then you also have these salt products that are being formed at the cathode, which themselves are easily dissolved into an acidic solution as well. So, and then you also have a thin material of of material that is forming over this material. So you get like the blister essentially that is formed, this iron hydroxyl material or iron hydroxide material, which is formed over the cuff. So basically you end up getting an enclosed space, where it's basically just a giant vat of acid that is trapped underneath your artifact surface, in which the salt is essentially just catalyzing and feeding this material en masse and creating these deep, deep pits in this loss of material. And you can see what it looks like when the pits burst, is that you have these kind of just these holes of active corrosion underneath. So this is something we definitely look at to see if we find any of these things, because this is a really, really good indicator that we have a lot of salt problems when we see these blisters form, just because of the way they catalyze anodic and acid reactions within an artifact. Another example is that this is one I actually worked on, this really nice Roman fibula pin. You can see examples of these little holes that are forming the surface, because this isn't just an iron problem, it also tends to affect copper alloys as well. And one of the most well-known forms of that is bronze disease. So this also illustrates the fact that a lot of these chloride-induced or salt-induced corrosive activities can be very, very destructive for your artifact. This also doesn't just affect metals or just metals. This can also affect organic materials as well as compound materials. So artifacts that are made of more than one thing. A good way to think about this, a really common one is wood that has been buried in a marine archaeological environment, especially one that has very little oxygen in it, like an anaerobic environment that, say, it gets buried very quickly under the mud and the sand and has very little access to oxygen. Whereas in most conditions, this would actually really help preserve your wood. If you have a particular type of microbe called sulfate or sulfur-reducing bacteria, you start to have other problems, because this type of material, they don't need oxygen to survive. And part of their metabolic processes is they produce hydrogen sulfate. And this hydrogen sulfate is illustrated in this micrograph as this sort of white material that is kind of coating the inside of the cells of your wood structure. And this is okay on its own. It's not the greatest thing to have sulfur in your wood. It definitely is a little stinky, for example. But where we really get problems is if you have other material in your wood. It's not just a piece of wood, it's a piece of wood planking that has nails in it, for example, or other types of metal hardware, especially iron, because that iron, is corroding in the saltwater environment, as we've discussed. And some of the products that are going to be made at the cathodic site are going to be iron sulfates and iron sulfides, which are different types of salts. And after excavation, what can happen is that these salts, if they are exposed to high humidity, can go through all that acid anodic breakdown process and produce sulfuric acid, essentially, which is no fun for anyone, especially because wood is often treated with material called PEG. PEG is a bulking material that is really critical to help these artifacts kind of retain their shape to make sure they don't fall apart. However, PEG itself, like most organic material, is slightly acidic. So as you can see, it also continues to catalyze this iron degradation and the production of both acid as well as more iron salts that can be further broken down into acids, like hydrogen salt, sulfuric acid. A really famous example of this is the vessel, the Vasa, which is a Swedish warship that basically sank immediately after launch in a river. So it's an amazing vessel. It's very beautifully intact and actually quite well preserved. And it's been fully excavated. However, one of the problems they realized is because it was so well preserved, it was most likely in an anaerobic environment, which means there's a lot of sulfate reducing bacteria that basically breathed all over them, impregnated it with sulfur products that then became iron sulfites and iron sulfates, salts that then upon treatment with PEG and also exposure to atmospheric humidity started to have some very major issues when it came to sulfuric acid damage. And one of the ways they're addressing this is trying to kind of after the fact try to remove those iron salts from the material. So you can actually see an example here. This is an example of wood from the Vasa before it was treated for iron salt contamination and after. So you can definitely see there's a difference. There's color, there's surface texture. You can definitely see where some of the wood has been eaten away and broken down. So that's a good example of that. And then there is also not just the chemistry that is happening, the fact that we are having these electrochemical cells form in which the electrolytes are helping to complete those cycles as well as these acid attacks. We also just have the growth of basically corrosion products themselves, because much like we talked about before with just straight up salt crystals and ceramics, you can also have the growth of corrosion products. So the things that are forming at the cathode occurring inside the artifact in unfortunate places. A good example of this is a material called acagonite or acagoniite, which is a very aggressive type of iron chloride. It actually only forms in high chloride concentration areas. So you can imagine those little pockets of moisture where I was talking about earlier, where we have basically hydrochloric acid forming and all this chloride that is forming. A lot of times the product that is being made at the cathodic site there is this material called acagonite, and it's actually incorporating the chloride into itself. And it's also attracts chlorides to it sort of weirdly. So it has chlorides kind of in its structure, but it also has chlorides that are kind of stuck on the surface. So it's kind of like a magnet for other chlorides. And the stuff very, can happen on a surface level, but it often very much happens, especially with wrought iron material inside the artifact. So this is sort of a diagram pointing out all the areas where acagonite might grow along the grain structure of a wrought iron nail, for example. And you can sort of see as this crystal grows, it tends to pop off part of your artifacts. So you're losing big chunks of your artifacts. And I've seen this be very, very aggressive to the point where your artifact is literally just dust if it goes untreated, just because this material is, salts are, just because they penetrate so deeply into the artifact, they can be very, very hard to fully deal with and remove. So even artifacts that have been treated, we still often have these types of problems. This is also an example, affects copper as well. Bronze disease is kind of an umbrella term for different types of material that affects bronze, but really any type of Catholic copper alloy can be affected. And it is both that sort of acidic pitting action that I mentioned earlier, but it also has to do with the formation of chlorides in chloride-based corrosion products of copper alloys that occur in unfortunate areas. So this is an example of this illustration. So you have your copper alloy base metal, you have the formation of copper chlorides on the surface. It forms a material called nantokite, and nantokite forms essentially underneath other layers of corrosion. So your copper oxides, your copper chlorides, these things are very normal forms of copper corrosion. We often sometimes purposely try to create them. That's what a patina is. A patina is essentially trying to artificially create corrosion on a surface to change the color or to give it better products, because not all corrosion is created equal. Some are very stable and nice to look at. Nantokite, however, is not very stable at all. And since it essentially forms underneath your more stable areas, as you can imagine, it can be very problematic when it starts to dry out, and then you might have an increase in relative humidity, oxygen, etc. Maybe your surface is a little cracked. Maybe there's little, there's already some pitting corrosion happening because of the other types of salt damage that are occurring. Water is getting in there and essentially crystallizing or solubilizing and then recrystallizing, and you have these other types of salts that are forming that are still transforming. Nantokite is one of those kind of half reacted type of things that will continue to transform and react as it's exposed to increasing levels of both chloride as well as humidity. So as you can see, those eventually grow as well and can erupt through your surface and break apart your artifact as well. So it's the same fibula that I showed you earlier. So not only does it have these pits, but you can also see in this very large area of loss where you just have this very kind of mint green fluffy stuff that is directly under this nice patinated layer, which is the surface we want to try to keep. So this is an example of sort of that manticate based other types of chloride transformation that are just expanding rapidly underneath the surface of your artifacts. All right, so that was a very, very long-winded way of talking about the different types of damage that salts can do. So hopefully you understand now why salts are such a huge problem and how, if they're left to go unchecked, they can actually destroy your artifacts. So what do we do about it? Well, first of all, if we're on an excavation and these are freshly excavated artifacts, we're taking them directly from the water site or the coastal site where they've been buried, and we get them wet, we try to keep them wet. Until we can safely dry them. This prevents that salt from recrystallizing as the water evaporates, and also just trying to keep, and also changing their environment too much to try to slow down other types of degradation. So we also try to slow down degradation through environmental control. So things like, yeah, this is correct. So we also try to keep them, oh, sorry, this is not in the right order. Apologies, that was not in the right order. Okay, so just to kind of, all right, so what do we do about this essentially is the big question. So we keep things wet when we initially get them until we can safely dry them. So to safely dry them, we first have to essentially try to remove the salts if we can. So just to remind you of how the salts get into there. So we have an artifact that is essentially a semi-permeable barrier on itself. It is not full of a lot of salts initially. It becomes full of salts by being in a salty environment that then diffuse into the artifact. So essentially to address this, we want to remove these salts. So we essentially want to reverse this. We want to remove the salts and literally suck them out of the artifact as much as we can. And we do this traditionally through a very simple method. It is a series of freshwater baths. So essentially we put our artifacts into water and we slowly let diffusion run in the opposite direction because we're hoping that our water is less salty than our artifact. And over time, the artifact will basically let go of its salt on its own. However, this is often not the case as our tap water has other things into it. It has microbes, it has other types of dissolved salts and dissolved minerals in it just naturally. So these can sort of, that all are kind of running on their own concentration gradients. And this can kind of slow down the process because there's just other things in the way. They're basically competing for that pore space in their artifact, trying to get through and trying to jostle each other to either get into the artifact or out of the artifact. So this really slows down our rate of desalination and can complicate it if it's basically the water around it is too salty of its own or has too much other stuff in it that our salt cannot effectively or efficiently leave essentially. So to deal with this, we often use water that has been treated already. So it's water that has had certain parts of it removed. I use reverse osmosis water. Some people use deionized water. Some people even use just distilled water. We can make our own, as I think I suggested earlier, that you can buy like household equivalents of basically water cleaning apparatus that can basically pre-filter your water and remove this. Distilled water and our water take out most of the microbial life as well as a good deal of sort of the competing salts and the other mineral content of your water. And then distilled water, as it says, or deionized water takes out basically all the ions that you can possibly count, leaving an artifact that has a much better success at achieving a gradient that is good, that is efficient, etc. And that we can basically more effectively remove that salt. Another problem we often run into is the fact, especially when it comes to metals, is that they come covered in a layer of either overburden. They come covered in concretion or just very kind of loose kind of matrices of sand and corrosion. Yes. Ooh, that's a good one. A solid cast iron anchor can take years, especially just moving passively desalination. If we're just putting it in a bath, a freshwater bath, that could take decades sometimes just to passively desalinate it. A lot of iron artifacts, especially if they're cast iron, which means they're more robust, we have other methods of sort of speeding that process up called electrolytic reduction. We're basically going back to sort of that galvanic cell I showed you earlier. We basically make an electrolytic shell, which is essentially the reverse of the galvanic shell. Where basically we essentially create our own circuit using DC electricity to essentially reverse the corrosion process and also create a much steeper electrical gradient between the bath, essentially the solvent that it's all sitting in, and the artifact itself. But good question. But just passively, basically the larger an artifact it is, usually the longer it's going to take, especially if it's something like iron or a metal that has kind of taken that artifact, it's partially corroded, and taken those salts and sort of incorporated it into itself. And they're not just, hanging out in the artifact. They are part of, the corrosion products in some cases that are kind of replacing the metal structure of the artifact. So it could take a very long time, but we do have methods of trying to speed it up in most cases. Well, it can, for instance, we have Canon here that if we just let them passively desalinate, they can take over a decade in some instances. By using electrolytic reduction on them, we can decrease that to 5 or 6 years. And there's so it can help a lot, but unfortunately, not all our artifacts are suitable to that methodology. They're just not very robust. Electrolytic reduction has a lot of positives, but it does have some risks associated with it. And also just logistical concerns, like it's not necessarily practical to put an electrode on every single wrought iron nail you have from the site that maybe has thousands. So you might have one, power source or something that is trying to form electrolysis connection with, multiple nails on one line, essentially, and you kind of decrease the further you get the positive effects and sort of the power of the electrochemical, the electrolytic reduction is kind of weakened as you go along a line. Sorry, I'm not expanding. I actually have another talk about specifically electrolytic reduction and sort of how that works. If you're interested, please come and talk to me afterwards. I'd be more than happy to go into that with more detail, but I am getting notified that I should probably keep on topic right now. But very good question. I will definitely go into that at a later date. So this is just talking about passive diffusion-based desalination, essentially. But to kind of get back to that, we have our iron where we have overburden that's on it. We first need to often clean that overburden so we have a more direct interface between the actual artifact and basically the bath that it's in, so we get a better desalination rate because we don't have all that other stuff in the way. But doing that often re-exposes your artifact to oxygen and, of course, moisture and other agents that affect corrosion, acids, salts, etc. And what happens is that we have all this re-exposure to water, obviously, if it's going back into a bath, oxygen, CO2, which might be diffusing into your solution and acidifying it over time. So you often end up getting corrosion called flash corrosion as well. And obviously, we don't really want to put our artifacts in a situation where we're actually inducing corrosion. So we try to deal with this by creating a buffer. So essentially, we add a basic material into our desalination bath when it's something like iron that is really affected by more acidic conditions or really more at risk for things like corrosion, which are very destructive and very fast. And essentially, these kind of are able to buffer or absorb that sort of basically take up the errant hydronium and hydroxide, or no, hydronium and hydrogen ions that are then kind of milling around because of the corrosion changes. So that is one way we sort of try to protect our artifacts in solution so that they can desalinate more effectively, and so the desalination process itself isn't more destructive. So we keep doing these baths until essentially our baths reach an equilibrium, until essentially diffusion has essentially shut down because there's equal amounts of your dissolved particulate both inside the artifact as well as outside. And we test this by using different types of methods. We use little handheld TDS monitors, which is sort of a very generic way of looking at total dissolved salt content or total dissolved solute content. So it gives you a very indirect and kind of general idea of how much stuff is in your water. And essentially, Once that number plateaus, we know to change out the number. Sometimes we want to monitor very specific salts because they do make specific meters that detect individual salt ions. For example, we for a lot of our really large scale iron artifacts, we'll use chloride specific meters. So instead of just kind of giving you a general idea of what's in your water, these tell you very specifically how much chloride ions there are in your water at a given time. I often use a very simpler form, these QuantLab sticks, which essentially have a silver sulfide solution inside them, which where they're in contact with chloride ions, essentially have a reaction that changes color on a measured little bar thing that you can see here, and create basically a color change up to a certain basically calibrated unit of measurement. So we kind of get an idea of how much chloride is in something. So it's sort of in between these two methods. That's how we keep track of our solutions, so we can make sure to have a good concentration gradient going and having effective, efficient rate of diffusion happening so that it doesn't take 10 years. These are also ways that we try to speed it up by making sure that our baths are changed out as often as is feasible in terms of resources to try to keep basically the diffusion moving essentially. There are also maybe instances where we do very localized forms of desalination. You might have artifacts that have been out of water for a while, and you're really kind of concerned about putting them back into a full bath and immersing them. So you might treat salts very locally. Maybe it's just a couple spots that you're noticing salt efflorescence on ceramics or corrosion problems, in which case we'll do something called poulticing. And a poultice is a combination of a material that is very porous, must be more porous than the material that you're treating. So things like paper pulp, clay, other types of fillers like methylcellulose and fabrics, sometimes even gel materials are porous enough to be used. And this is added into some sort of liquid. We often use water, sometimes you use other types of solvents. And again, it's important that whatever you're making, your poultice has more poles or more holes in it than the artifact that you're treating, to make sure that you are essentially pulling the salts in the right direction, that you're not actually making them go further into the artifact, that you're actually basically enticing them to come into the more holy artifact, to the more holy material. And essentially what happens is you put your poultice against the material. That went a little too fast. The water evaporates over time, and that evaporation actually causes the salts to essentially be pulled out of the artifact. It's very cool. And this is called a capillary action. So this is basically another one of the fabulous properties of water that I didn't really get to go into. It has to do with hydrogen bonding and things like that and how that works. But it is a very localized way of treating our artifacts when they have salt damage, often applied to ceramics. So desalination aftercare. So after desalination, our objects are still wet. So we have to do things like dry them appropriately. Things like wood or things organic, this might involve using a freeze dryer, which basically allows us to remove the water without causing a lot of physical stress, without actually inducing that capillary action that I showed you was a benefit for the poultice. It can also be a drawback for a lot of artifacts because it is a lot of stress on the artifact that can actually cause them to crack or break or shrink, kinds of all things that we don't really want to happen to them. So a freeze dryer essentially sublimates. It causes sublimation. It basically causes the frozen, first you have to take your artifact, put it in like a chest freezer for a few days, basically freeze the water content. That frozen water then is sublimated inside your freeze drying chamber, because basically you're treating it at temperatures so low that essentially it skips over the liquid phase and goes right to a gas. So basically it goes from a solid to a gas in one step, which means you're skipping the liquid water phase, which means you have no capillary action damaging your artifacts. For things that aren't freeze dryable, like metals, we often have desiccation chambers, or basically chambers that we control essentially the humidity or how wet it is in there. And essentially these are very slow processes. Well, we'll start them off at a high humidity, so something with a lot of moisture in the atmosphere, and then over time gradually decrease that humidity until it's a dry ambient temperature. So that's one way of very slowly drying your artifacts. If you don't have a freeze dryer, for instance, or if you have an artifact that's like a cannon or a large iron artifact, for example, this is a good way of doing it. We also try to, for the future care, kind of eliminate or mitigate or lessen contact with moisture in the atmosphere, oxygen in the atmosphere, other things that involve corrosion. Because there's no guarantee that we're going to be able to remove all the salts in our desalination either. We try to get them as low as possible, but as we've shown, a lot of corrosion products have salt either like in their structure, or as we kind of talked about earlier, not all our desalination methods are necessarily effective just because of the bulk of the artifacts. Some things are too delicate to go through electrolytic reduction, for example, if they're iron. So we often get outcomes that are very kind of hard to predict, and no artifact is exactly the same either. So even electrolytic reduction has a high level of variability just because there's so many differences in the composition of our artifacts and how much of them are still iron, how much of them are corrosion product, and just sort of the quality of the preservation state as well can be hard to predict. So, we try to do these things kind of cabulated to the best as we can to the artifacts, but no artifact is one size fits all. So unfortunately, we do have situations where we're not able to get all that salt out. So the next best thing we can try to do is try to prevent contact with things like atmospheric moisture, which will do things like, resolubilize our salts, and then have them recrystallize or basically put them into a salty solution in little reservoirs in our artifact that can then induce corrosion, et cetera. And we do this through a variety of methods. We have chemical treatments, things that basically we treat the artifact with that react with the material itself that creates a very, very insoluble, impermeable barrier. Things like tannic acid and benzyl triazole are two things that we use for iron and copper specifically. These are materials that essentially react with the iron or the copper, and they basically create a new product, like a corrosion product, essentially almost, that essentially sits on top of the artifact, that is bonded to the artifact, that prevents a very solid barrier between the air and the moisture and the artifact and the material underneath. We also use other types of coating applications. This can be anything from painting systems to the application of acrylics or acrylic almost adhesive materials or resins or other types of barrier layers that you might use on anything from your boat to your car. We have versions of that we often use on our artifacts as well. And then one of the things we're really trying to kind of advance in conservation is how well we can actually control the environment itself. So, how well can we eliminate or reduce or control or stabilize our RH versus our temperature, et cetera. So these involved introducing things like desiccants into your storage area, your exhibit area for your artifact, things that basically can absorb moisture from the water, that can absorb pollutants from the air, et cetera, as well as more active forms of air conditioning, essentially. So, you might have actual dehumidifiers built into your cases. You might, in some really, really fancy circumstances, have like actual air conditioning units that are built into your cases that you can control things like temperature and humidity overall, or for building wide as well. You might also just use good old fashioned, the bucket dehumidifiers that you find in your basements, et cetera. There's all kinds of different methods that we can use to try to improve environmental conditions to try to protect these artifacts long term, so that even though our salt outcomes could be very unpredictable in terms of actually how we remove them, and if we're efficient in doing so, we can still try to control some of the effects that having salts in our artifacts can have on the artifacts. All right, so thank you very much for listening. I do want to remind you that our next Maritime Heritage Series presentation is coming up on February 23rd. And that will be given by my good friend David Bennett, our maritime historian, and that will be a talk entitled North Carolina's Antebellum Shad and Herring Fishery. So please join us on the 23rd at 11 a.m. And if you like this presentation, I will have another one in May 11th, where I'm talking about concretions, how they form and how we deal with them. So I got into a little tiny bit here, but this will deal with them in more depth. Thank you very much for your time. Does anyone have any questions? Yes.
You mentioned in one of